Welcome back once again to our video lecture for ABE164. In the previous videos, we talked about the DC systems, those types of systems wherein the current doesn't change with time, or we can say a constant current all throughout the time interval. Recall this graph of the current with respect to time. And when we are saying DC, the current is just constant all throughout the time interval, or the time interval for the entire analysis. Although the topics on DC systems, actually there are topics involving transient effects, like for example in capacitors or inductors. Before we can reach that maximum storage of energy, and somehow there's going to be some transient effects. But we didn't deal with that because it's entirely the scope of a course in electric circuits. Okay, and also we did basic analysis on the circuits involving either purely resistors or purely inductors or purely capacitors. But in practice, it's also common to find combinations of both the resistors and capacitors. We call that RL circuits or RC circuits, resistors and capacitors, and also the combination of all the three passive elements, RLC circuits, resistors, inductors, and capacitors. So that means that there are still many other topics that we haven't discussed because, as I've said, it's under the scope of a course in electric circuits, specifically DC electric circuits, and also a lot of methods. There's still much more to learn about that, but it's beyond the scope of our course. Now, in this topic number 4, we'll be discussing the AC systems. When we're saying AC systems, we are referring to currents that alternates. That's what AC stands for, alternating current. So that alternates, or that current alternates with time. And when I say alternates, at some time interval it is, let's say it's positive, and then at the time interval it's going to be negative. So this is one type of alternating current that alternates, right, from positive to negative. But there are still many other waveform for alternating currents. So specifically what we're talking about when I say alternating current, in this lecture we are dealing with sinusoidal, or I mean those currents with sinusoidal waveforms. Okay, so that's our topic for for this topic number 4. Okay, so the subtopics for under this, we'll be talking about the of course introduction of the AC systems, and then we'll talk about the sinusoids, and then the phasor concepts, and lastly we'll talk about the basic operations of the complex numbers. Okay, so to begin, so one important reason, or one of the important reasons for concentrating on the sinusoidal AC is that that's the electrical power supply from the power generating plant or power generation, or we can say the electrical power from the wall outlet of your room. That's an AC supply. And so power systems, it's transmitted AC supply, and also in communication systems there are also applications of this sinusoidal AC. Right here in the figure we have a generator, and depending upon the type of generator, whether AC generator or DC generator, so we can have this AC output. And as we have said also in the generating plant, so if we have power plants, so it could be coal power plants or whatever power plants, it has to drive the shaft of this generator. So we have generators here as well. So mechanical power input to drive the shaft, and then the output here is an electrical energy in the form of AC supplies. Also, we have wind turbines. So it's the same. Actually, it lies on this device right here. It's all about the rotation of this mechanical shaft in order to produce some electrical supply. But in this case, when you say wind turbine, the rotation or the source of power is through the wind force on these blades, and then that because of that, then the blades or the shaft where the blade is attached, it's going to rotate because of the wind action. Okay, so right here there's going to be some generator, something like this, and of course some other mechanical devices. Right here we also have the photovoltaics. The photovoltaics, they are devices that converts the energy from the sun. So the light energy from the sun, it converts into electrical energy. But right here the output is DC, but because of this device, this is what we call inverter. So inverter, it converts the DC electrical DC electricity into AC electricity. Okay, so there are actually a lot of applications of these AC systems, as I've said, primarily for power systems and then also in communication systems. Now, the basic operation or the principle of operations for this, how this AC output is generated, is based on the Faraday's law. And the Faraday's law basically says that whenever there's a coil of wire or a conductor rotating or moving through a magnetic flux or cutting a magnetic flux, it induces an EMF or electromagnetic force that's related to the voltage. Okay, so again, a coil of wire moving through a magnetic flux. So right here in the figure we have these magnets. We have the north and south magnets positioned as shown, and because there's a magnet, then there's gonna be some magnetic flux, right? So there's magnetic flux right here. Now the red one or the red lines in this figure, that's actually a coil, or let's say a conductor, and that conductor actually cuts through this magnetic flux because this conductor is being rotated. This is the shaft, so it's being rotated. So because it rotates, then it's cutting the magnetic flux. So as it cuts or as it moves through this magnetic flux, then there's gonna be an output of this electrical supply. So here's the output, and that output is AC. Right here in the figure we also have another maybe we can say a cross section of this rotating coil that cuts through a magnetic flux. We have these north and south magnets, and because of that north and south, then there's going to be magnetic flux. And you can see here actually we have magnetic flux, and our conductor or rotating coil of wire is these red ones. So it rotates. So as it rotates, then it cuts through, and you will also notice that, let's say here, we'll divide this into 4 quadrants. We have 0 here, 90, 180, and 270. So the cutting of the coil, if the coil is in this position, it cuts through. Actually, it's parallel. Maybe you can say parallel to the lines of. This action is parallel to the lines of magnetic flux. But if it's right here at 90 degrees and 270 degrees, the cutting of action, you can see is perpendicular to the magnetic flux. So that is why there is a waveform such as this. Okay, so going back again, let's say we'll start from 0. So once it is 0, once the action of the coil is parallel to the line of the magnetic flux, then our generation of voltage is just 0. So it's right here. Now as it moves, as it rotates counterclockwise, then it starts to cut the flux until it reaches this 90 degrees. So the cutting is perpendicular. So that's the time wherein it will reach its maximum. Okay, so as it continues to rotate, then it goes to this 180 degrees. It's going to be parallel once again to the magnetic flux or lines of magnetic flux. Then it goes back here to 0. Okay, and from 180 to 270, then again it's gonna reach its maximum because it's going to be perpendicular to the lines of flux. That's why we have here a maximum again, but at a negative direction or negative sign, because we are here in the south pole. And then again back to 0. So it just repeats itself. We'll see here here that we have a sign, a positive sign, and we can also have a negative sign. So that's the generation of the sinusoidal waveform from this AC generator or alternator. Okay, so this one, maybe we can say from an AC generator, or the term is also referred to as alternator. Okay, so now let's move on to the sinusoid. The sinusoid, when you say sinusoid, we are referring to the waveform. It says here that the sinusoidal current, usually referred to as alternating current, but we've said already that when you say alternating current, that's a general term for any types of current or any type of waveform that alternates. Sometimes when you say sinusoidal, sometimes we mean alternating current. So it's a type of current that reverses at regular time intervals and has alternately positive and negative values. We already discussed this. There's going to be positive, negative, positive, and then going back to negative. So it reverses, but how fast does it reverse? So there is a parameter later on that we'll study in much detail, what we call frequency. So frequency is something like how fast does it reverses. Okay, so if we have this wall outlet right here, let's say reversing current, then let's say here's our wall outlet, and then we at some point in time, let's say here's the positive, and then the other one is negative. After some time interval, the negative will be on this side of the socket, and then the positive will be on the other side. And then after some time interval, then it's gonna be back again to plus and minus. So this reversal of the current or the signs actually relates to the reversal of the direction of this current. Okay, so in this circuit right here, so at some time or at some point in time, the direction, let's say, is going to the right. Let's say from positive, enters the positive direction. Then after some time, this will be the positive, and then this one will be the negative. So it goes back. It goes to the other direction. Okay, so how fast does it change its sign is actually related to this frequency, in which we will discuss in much detail later. Okay, so technically when you say a sinusoid, it's a signal that has a form of either sine or cosine. So whether sine function or cosine, sine waveform or cosine waveform, that's what we refer to as a sinusoid. Now when we say sine function, recall that the sine function, its waveform starts from 0. So here's the waveform, and let's say when we consider a unit circle or a circle with a radius of 1, then that's just going to be the maximum right here. And this will be the waveform. When we say cosine, the starting point is at this peak value. Let's say unit circle once again. So this is a radius 1 or a magnitude of 1. But the let's say supposedly they are the same in all the parameters except for one parameter, which is just simply the shifting. So there is the difference between the sine function and the cosine function. It's just simply the cosine is somewhat shifted type of functions. But if you superimpose this, actually they are almost the same. They are actually exactly the same, except for this shifted version. So therefore, that means that we can derive equations using sine, or we can also derive equations using cosine functions. But in this lecture and in some other reference texts, Sometimes the reference is based on the cosines, and what that means is that if, for example, in the problems or in the homeworks or exams, if a function is given in terms of sine, it just have to be um, transformed or translated to cosine function and then do the operations. Okay, so again, in this lecture, or in our lecture, we will be considering the cosine functions. So considering the cosines, the mathematical expression is this. So some function of time, here's our variable, and let's say we are talking about the voltage. So whether, by the way, whether voltage or current, it's gonna be the same thing when we're talking about the function. But for discussion purposes, we'll just limit. For now, we'll use the voltage as an example. But again, the terms that we'll be discussing here, let's say the amplitude, the angular frequency, the time and phase, it also applies to this current. Okay, so for these mathematical expressions, we have this voltage function as a function of time. So that means that the voltage actually changes with respect to time. So why does it change? Because if here's our graph of time and the voltage, so we have this cyclic functions. So at some point in time, this will be the value, or at some point of time, this will be the value of the voltage. So that's why it's a changing variable or entity or quantity. Then it's equal to the Vp, or the maximum voltage, or the magnitude of this, or we can also say the amplitude of this, times the cosine of the angles. But the angles right here, we have a lot of terms. The angle includes the omega, and that's what we call the angular frequency. So how fast does it rotate, radians? The t is in the time in seconds, and the theta is the phase angle or phase shift in degrees. Okay, so we'll discuss that one by one. Here's actually the waveform of that sinusoid. We have a graph of time along the horizontal direction and a graph of voltage along the vertical direction. So the waveform, it goes to some peak values in the positive, and then goes back again to zero, and then some peak values the negative, then goes back to zero, and goes so it's a cyclic waveform. So this peak value is what we call the let's say the V peak, the peak voltage. So it's the maximum value in the direction along the positive. And you will notice that because it's a repeating waveform or cyclic waveform, let's say here's our we'll start from this point. So it goes to the maximum, goes back to zero, goes to a negative maximum, then goes back to zero. So somehow there is a the waveform repeats itself, or at some point, right? So from here to here, that's what we call one waveform. Or maybe let's say if this is our reference point, let's say here's our reference point. So from here goes to zero, goes to maximum positive, and goes to zero, and then goes back here. So from here to here, you can say that it's also one waveform, one complete waveform, depending upon our reference point. And that waveform is what we call cycle, right? So that's what we call one cycle of waveform. So take note of that. So how many cycles, let's say at some time, in some time interval. So we'll discuss that in the next, maybe right here. We'll discuss it here. Okay, so next one is the amplitude. The amplitude, that's the term wherein it's actually the distance from the horizontal axis, or from the time axis, or zero actually, from the zero voltage to some maximum value. So that's the amplitude. Again, from the zero voltage, or from the horizontal axis, you can say, to some maximum values. So positive values. That's what we'll sometimes positive V. And from this going downward to the maximum in the negative direction, that's what we label as negative V. So it's the peak value in the negative direction. So this is a peak value. By the way, when we say amplitude and V peaks, somehow they are essentially the same, because the peak, we are only referring to the point, but it's actually the same magnitude, right? And the distance right here, that's still the maximum value, or the magnitude of the maximum value. Okay, so peak, the distance from this peak value to the, I mean, peak value in the positive to the peak value in the negative, that's what we call the peak to peak value. Okay, so the point, it says here, the point value at which the waveform repeats itself is what we call cycle, and we have discussed this already. And the time the waveform repeats itself, so the time, let's say here's again our reference point, and then it goes back to its original point. So the time that it completes its one cycle is what we call the period T, right? So take note of that. And the number of times the cycle repeats itself is referred to as a frequency. Okay, so frequency, how many cycles does it change along the time interval that we are considering, right? So here, that's one, then another, here another cycle. So let's say this edge right here, this is the time axis, right? So time axis, and also time axis. And let's say this one is 0 second, or time 0, and then here is 1 second. Then here is 0, and this one is 1 second. This one is 0, and here is 1 second. Okay, so when we say a frequency of 2 hertz, so that's the units of frequency. By the way, the mathematical expression or relationship of the frequency is just 1 over period, 1 divided by the t, or 1 over the period, and the units is in hertz, or Hz. That's the units. When we say 2 hertz, that means in 1 second it has to complete a waveform of it has to complete 2 waveforms. Here's one waveform, here's another waveform. So that's 2 hertz, 2 waveforms in 1 second. When you say 1 hertz, then there's gonna be 1 waveform in 1 second. So it has to complete 1 waveform in 1 second. When I say 0.5 hertz, that's basically saying that in or the 1 second, 1 waveform is completed in 2 seconds, or you can say half of the waveform is completed in just 1 second. So it will complete after another second, so 2 seconds. So that's the visual illustration for this frequency. Now the AC supply that we have in the or provided by the utility company is in our country we have 60 hertz. So that means the cycles, or the number of waveforms, there's actually 60 repetitions or 60 reversal in 1 second. So that's actually happening very very fast. That's why 60 hertz, or that's what 60 hertz means. Okay, so moving on, we have this angular frequency. Recall here in our expression that we have the sinusoid Vp cosine. Take note of this. This one is in angular frequency rather than F. Let's write here angular frequency. The angular frequency is related, or let's say it's a measure in terms of the radians per second. So somehow it is related to the frequency, except that um, it describes, or it's a measure of the angle swept in terms of angle swept per unit time. So that's why this is radians per seconds. Whereas the frequency is cycles per second. So somehow this is linear. Uh, this is linear, and this one is angular. So they are actually related by this equation. Omega is equal to 2 pi f, because let's say here's our starting point, point 0, and along the linear, or this waveform axis, we have the 0 right here. So from 0 to 90, this is the point. Then from 90 to 180, this will be the point. And then from 180 to 270, this will be the next point, and then back to 0. So that means that the entire circle, or the angle to be swept for the entire circle is, in terms of radians, this is starting from 0. Then we have this pi over 2, and this one we have pi, and right here we have 3 pi over 2, and here we have 2 pi. So that's why we have this 2 pi. Now in terms of degrees, this is 0, this is 90 degrees, this is 180 degrees, and this is 270 degrees. Okay, so once again, the angular frequency is not the same as the frequency, because one is talking about the radians, or the angles, or it's a measurement of the angles, rate of change of angles with respect to time, or how fast the angle is changing. Whereas when I say frequency, that's how fast, or how many cycles, or it's a measurement of the number of cycles the waveform repeats itself. That's the frequency. Okay, next one, the phase shift angle. So right here, recall that we have this parameter right here, an angle phi, or phi, and that stands for phase shift angle, and it tells where we start measuring on the cosine. Usually the reference, or the starting point, is based on some arbitrary values, and usually the reference is the 0 here, or the, let's say let's say we have a sine waveform, so somehow it's related to here. So that's why our reference is the 0. When I say phase angle equal to 0, if this value right here is equal to 0, that means that the waveform looks like this. So that means that at time, let's say here's our time 0. So at time 0, where we started our measurement, the value of the waveform is 0 at that point. Okay. So again, when we say phase angle, or phase shift is 0, that means that at time 0, when we're taking this time, starting our measurement, then at t0, the magnitude of this parameter right here, or the voltage, is 0, based on this waveform. And when I say a positive phase shift, now it looks something like this. So there is a shift. The 0 value is right here. But again, why is it positive? Because to me, I look at the values right here. So once it crosses this time 0, when we start measuring our time, the value of the voltage is at some positive values. So that's why it's a positive phase shift. And see, the phase angle, recall that it's about the shifting, or how far is it from some reference waveform, or from some reference values. So starting here, right, so how far is it to let's say we have a waveform right here, or our reference waveform, because later on we'll be having waveforms, let's say a voltage waveform and then the current waveform. But for now, we only um, draw the voltage waveform. So at some reference, that's the phase shift or the phase angle, positive. And for the negative phase shift, so at time 0, this is t0, what's the value of the voltage? The value is at some negative values. So that's negative phase shift, and the shifting, this is the phase angle. Alright, so now moving on, all terms discussed thus far can be applied to any alternating waveform. In electrical context, even if we just talk about the voltage waveform, let's say here's the voltage source, but it is applicable as well to the sinusoidal current sources. And later on, these two waveforms gonna mix so that we can form another waveforms like the power waveform.